Okay, let's have a look at the quiz that went out in weeks 5 and 6, which was a series of multiple choice questions. First one was, what do I describe as the essential paradox of probability? Point I made several times in the lectures. Large collections of individually unpredictable random events are very predictable. That's just the law of large numbers. If you toss a coin once, you don't know if it's going to come up heads or tails. If you toss a coin 1,000,000 times and it's a fair coin, about half the time it'll come up heads, about half the time it'll come up tails. Even though after each individual toss, you don't know what it's going to do next time. Everything must eventually happen. Afraid not. Pigs don't fly. Probability exists only in the mind, not empirically. That's a topic of some extensive philosophical debate. Probability most of the time exists only in the mind. We make estimates or guesses about what we think is likely to happen in the future, for example. However, probability also exists empirically. We can look at a series of, for example, random coin tosses that have already occurred, and we could still use probability to describe them. And in that sense, in the sense of frequency of occurrence of events in the long run, probability could be said to exist empirically as well. Chains of cause and effect exist only in the mind. Our theories about cause and effect might exist only in the mind, but it looks as if there's something that is awfully like causation happening out there in the real world. And this is probably too difficult, it's just a nonsense answer. A good definition of random is not capable of being predicted. Having no pattern is not quite the same thing in that it could be possible to have something that was patternless but nevertheless predictable. So the safest definition of random is something that is unpredictable. Random events can nevertheless have a cause. It's just that the effects aren't always, the nature of the effects in detail aren't predictable. So that something causes a radioactive isotope to decay into some other kind of element, but we couldn't predict which individual atoms would make that change at any point in time. Random's got nothing to do with being instantaneous or endless, even though I might go on about it endlessly. This is just to check whether you've been doing any of the reading. The right answer is 8 by 10 to the 67, which is an incredibly large number. If somebody was properly randomly shuffling cards and dealing them out time after time, on average they'd be at it for a few million years before they would come up with two identical sequences. The law that allows us to understand probability, as I've mentioned earlier, is the law of large numbers. I don't know if Jude Law knows anything about probability. I suspect not very much. As far as I'm aware, there's no such thing as Bernoulli's law, and the law of diminishing returns is about something else altogether. In order to describe and understand probability, we need the concepts of a trial, outcomes to that trial, the definition of those outcomes in terms of success and failure, and sample space as the description of all the possible outcomes. Games of chance are good at modelling probability because they include random processes. Dealing cards, throwing dice, tossing coins, things like that depend on their chance element to make a game work beyond just the individual skills of the players involved. And then the reason that we use games of chance to illustrate aspects of probability is because they're nice and simple. Random processes in the real world tend to be rather more complex and messy and not so easy to deal with. That's why we use games of chance. Two events are independent when the occurrence of one has no effect on the occurrence of the other. In other words, there's no association between them. The fact that one occurs doesn't impact upon the probability that the other one will occur. That's the opposite of a situation where the occurrence of one is conditional upon the occurrence of the other, in which case the two events are associated. And whether or not one occurs before the other doesn't really have much to do with it. When I say something is conditional upon something else, examples might be let's think of something. The occurrence of becoming a parent is conditional upon one of the parents being pregnant. It can't occur without the other thing occurring. The two events are clearly related. They're not independent. The condition of being divorced is independent of the condition of being a parent. Some divorced people may be parents, others may not be. The two aren't necessarily associated. It would be an empirical question to see how far they were associated. Oh, sorry, I've jumped a couple of questions. If I throw two dice, how many ways can I get 6? I can get 6 by throwing a 1 and a 5, a 2 and then a 4, a 3 and a 3, a 4 and then a 2, a 5 and then a 1. So there's 5 ways. However, there's 6 ways of getting 7. I can get a 1 and a 6, a 2 and a 4. Sorry, a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, a 6 and a 1. In other words, you're more likely in the long run to get a 7 throwing a dice many times than you are to get a 6. Because there's only one way of getting 2 3s, that's both of the dice landing on 3. Disjoint is just another way for saying that two things are independent of each other. The probability of two independent events, two events that aren't conditional on each other, taking place is simply the product of their individual probabilities. If I toss a coin twice, the chances of getting 2 heads are 0.25, chances of getting 2 tails are 0.25. The chance of getting a head and a tail is 0.5 because there are 2 ways that I could obtain it. I could get a head on one toss and a tail on the second toss. I could get a tail on the first toss and a head on the second toss. But there's only one way of getting 2 heads and one way of getting 2 tails. It's a bit like 6s and 7s in the dice. These are just different ways of saying that events aren't independent. They're conditional upon each other, they're associated, or they're correlated. All just means the same thing. In a sample space, the sum of all the different probabilities must be 1, because that just expresses the fact that something must happen. They must be mutually exclusive. In other words, you can have 2 outcomes at once. And they must be comprehensive. They must describe every possibility. Otherwise, if they didn't describe every possibility, their sum couldn't be 1. Neatly fits together. Trial with only 2 possible outcomes is called a Bernoulli trial, after the mathematician who first investigated their character. And the binomial formula just tells us the probability of k successes in n independent Bernoulli trials for a long run value of p. Again, this is just to check if you've done the reading, and the famous Finnish study was one of the first pieces of evidence that suggested that there was a connection between early death caused by things like lung cancer and heart disease and smoking. David Spiegelhalter is the Winton Professor for the Public Understanding of Risk. And I suggested in the lectures that the most spectacular result of randomness in operation is human beings. They're a function of the operation over billions of years of natural selection and random mutation in evolution. A couple of billion years ago, we started off as an extremely simple single cell organism. And from one of those organisms, we are all descended. However, it did take a couple of billion years. That's it.